Alright, today's lesson is going to be on the Doppler effect. Uh, Maybe some of you have heard of this in real life. Maybe not the exact name, but the phenomenon maybe you've heard of before. And so that's it's going to be on the Doppler effect. But before we talk about it, let's go into a bit of review. What you're seeing right here are sound waves, right? So the speaker is stationary, it's not moving anywhere, and it's producing sound waves. And the sound waves go away from the center. And as you notice, the particles themselves, they don't move away. Right? The particles themselves, the air molecules, don't actually move anywhere. Rather, they just move back and forth, but they don't travel outwards. And so the energy of the wave travels outwards. So what exactly is a periodic wave? Again, we talked about this in the previous uh, three lessons. The wave of the wave is one entire up cycle and one entire down cycle. Okay, so that is the wavelength of a wave. And the frequency of the wave is, well, frequency isn't really described here, but the frequency of a wave is how many wave cycles occur in a second or a given amount of time. Right? And so if in 1 second there are two wavelengths occurring, two wave cycles occurring, well, you have a frequency of point of no, no of 2 hertz. Right? There are two wave cycles occurring in 1 second. That is the frequency. Right? So frequency is how many wave cycles occur in a given amount of time. So that video was played. Let's actually pause it for a second. That video was played without me telling you exactly what was going on. But now that it has played, what was being demonstrated was the Doppler effect. Right. So as the car started going towards you, towards the observer, and away from the observer, you hear a difference in the sound of the car horn. So let's listen to it again. And I want you to focus on the sound of the car horn. So as the car was going to the observer, going to you, going to the camera, you should see, or rather, you should hear that the car horn was getting a more higher pitch, right? It was like, okay, all right, that's enough of that. But you should see that there was a higher pitch as the car came towards you. And as the car went away from the person, the pitch got lower. And so let's listen to it again. So higher pitch. So as it passes you, there's a lower pitch. So exactly what is happening there, right? How does that happen with waves? Right? Because there's a reason why you hear a difference in pitch. So I want you to focus on the left GIF, all right? So the left GIF is more of like a 2D view of what is occurring with sound wave. And so the purple lines represent where there's a compression, right? Remember, in a sound wave, in a longitudinal wave, there's a compression of sound waves. So if you don't know what I mean, so where these air molecules are bunching up, right? That's compression. And where you see a lot of space in between them, that's rarefaction. So you kind of see these lines spreading outwards. Right? You see the lines spreading outwards. And so that's what is being represented on the left GIF. Right? Those purple lines are the bunched up waves, compressed waves. and they correspond to the top of this wavelength, right? The top is that's what it's corresponding to, and the bottom is corresponding to the space in between. So now let's take a look at the right GIF. The right GIF is a bit different. In the left GIF, the orange dot is your speaker, right? And so that speaker is stationary. But let's say our source of our sound is moving. Well, when the source of the sound is moving, you can clearly see on the right GIF that the waves that you see are different, right? The waves aren't even anymore. It's definitely different. On the right hand side, you see that the waves are more bunched up. On the left hand side, you see that the waves are more spread apart. And now we can make some sort of connection, right? Well, not yet at least, but I just want you to notice that there is this difference. And so it's a similar GIF now. It's actually the same GIF. I just cut it. So now you see that there's a back observer now. There's some person behind the source. And as the source is moving towards the front observer, the sound that the back observer and the sound that the front observer hears are both different. And that really depends on what you're seeing right here. How these waves look is why these observers are hearing something different. So let's move on. Let's talk more about it. So let's examine these two images. Right, let's ignore all the words for now. Let's examine these two images. So on the left image, it's basically just a screenshot of the source, the sound source moving towards the observer. And because the sound source is moving towards the observer, you see that there are all these bunched up lines. Right? There are more sound waves hitting the front observer as the sound source is moving towards the observer. But let's take a look at the second image. What's happening in the second image is a screenshot of the sound source moving away from the observer. So as the sound source moves away from the observer, these sound waves, there are less of these sound waves per given distance. Because if you look at this distance, right, this distance right here, this distance right here, when the sound source moves towards the observer, there are more sound waves. When the sound wave moves away, when the sound source is coming from a source that is moving away from the observer, the sound that the observer hears is a bit different. There are less sound waves that the observer hears. Let's go back to this image. Let's go back to this GIF, right? So if you notice that the source is moving towards the observer, there are more sound waves. But as the sound source moves away from the observer hears less sound waves. Less sound waves are reaching the observer. Less sound waves are reaching the observer. So let's take a look at number one. If the sound source is moving towards the observed sound waves will have what? Right? If you're moving towards the observer, there are more sound waves. So you have a higher frequency. You have a higher frequency here. Let's not go. So the sound waves that the observer hears has a higher frequency because as the sound source is moving towards the observer. Well, what about wavelength? What about wavelength? The wavelength is the distance between each of these lines. The wavelength is much shorter compared to this image, right? There's higher frequency here and there's shorter wavelength, and that must make sense. That makes sense because if you take a look at this formula right here, V is equal to frequency times wavelength. Well, if frequency goes up, then wavelength must go down. Now let's look at number two. If the sound source is moving away from the observer, the observed sound waves will have what? By the observer, it's going to have lower frequency, right? There are less sound waves that the observer is hearing, and the wavelength, the distance between the waves is longer. All right, so let's actually answer these questions. It's higher frequency, and shorter wavelength, and lower frequency and longer wavelength. So right there. So this is what you want to refer back to when you answer the homework questions. And so you might want to go back to these GIFs to kind of visualize it yourself, because you kind of do see here, as the source moves towards the front observer, the waves are more bunched up, higher frequency, shorter wavelength. But as the sound source moves away from the observer hears something different. He hears a lower frequency, but in a longer wavelength. So number 3, describe the relationship between observed frequency and wavelength if velocity is constant. Inverse relationship. There's an inverse relationship there. Number 4, and this is also something really important. The higher the frequency, the higher the pitch. The higher the frequency, the higher the pitch. So the lower the frequency, the lower the pitch. Now let's look at something different. Let's look at something different here. What can you say about the frequency? And I want you to look at this question here. What can you say about the frequency observed by the observer? So when the observer is still and when the observer moves towards the source, what do you notice? Right, the sound wave, the sound source is stationary. It's producing sound waves at regular intervals. But in this situation, the observer is the one that's moving. What do you notice? Again, the smiley faces light up when the sound waves hit the observer. You'll see that the bottom, when the observer moves towards the source, more sound waves are reaching this observer per second than the observer as standing still. So if the observer on the bottom hears more sound waves per second, the sound waves are a higher frequency, right? The sound waves that this observer on the bottom hears is of a higher frequency and a shorter wavelength than this observer. Kind of look at this more. Again, frequency is the amount of sound waves that occur in a given second. Feel free to pause or rewind. Now let's look at this one. This one is a bit different. The observer is moving away from the source. So what can you say about the frequency observed by the observer? And the sound waves are being produced at regular intervals. And the smiley face will light up when the sound waves hit you. And the person on the bottom, since he's moving away, these sound waves take a bit longer to get to him. So the frequency of these waves that the observer is hearing is less. So it takes more time for this person to hear each of these sound waves. So that must mean that these sound waves are of lower frequency, right? He hears less sound waves per second. And that must mean the wavelength is longer. The wavelength is longer and the frequency is shorter. All right. So let's actually summarize this in case you need to look at this as you're completing uh, your questions. When an observer moves towards the sound source, the sound waves the observer hears is of higher frequency and shorter wavelength. So as the observer moves away from the source, the sound waves the observer hears is of lower frequency and longer wavelength. And so that's what you can refer back to as you complete the questions. Right. Cool. That's not what I want to do. So let's take a look at light waves. So this is actually one of the ways we can tell whether a star or something is moving away from the Earth, moving towards or away from the Earth, is whether or not the color of the light is more red or more blue. Think about it. You have visible light from a sun, from a star, and that star is moving away from you. If it is moving away from you, that must mean that the wave of that light has a longer, rather, a less frequency, lower frequency, and a longer wavelength. That must mean that if you want lower frequency, longer wavelength, that must mean the color of the light is red shifted. It means it is more red, right? Because if we know that sound waves differ as you get closer or away from someone, the sound waves differ. It either has a different lower frequency or longer wavelength. Lower frequency or higher frequency. So as the star is moving away from you, there's lower frequency, longer wavelength, and the color is more red shifted. But if instead the star is moving closer to the Earth, that must mean that there's a higher frequency of light. That must mean that the light is more blue shifted, which means that it's going to be more blue, more blue. So that's one of the ways we can tell whether or not a star is moving towards the Earth or away from the Earth, depending on the color of the light. If the color of the light is lower frequency, it's moving away. If the color of the light is higher frequency, it's moving towards you. All right, cool. Let us let us solve these questions. Number one, the Doppler effect is best described as, and this is pretty much what the Doppler effect is, right? This is the Doppler effect. This is the Doppler effect. So it's gonna be D. Bending of waves as they pass by obstacles, you don't even know what that is yet. Changing speed. Not really, the speed is more or less constant. Oh, that's something else. That's called Snell's law, or law of refraction. But we haven't learned that yet. See? Haven't learned that yet either. It's definitely D. Shift in observed frequency and wavelength of wave caused by the relative motion between the wave's source and observer. That is the Doppler effect, alright? So number two. The car of a horn produces a sound wave of constant frequency. The car traveling at constant speed approaches, passes, then moves away from a stationary observer. Which graph best represents the frequency of the sound wave detected by the observer during the time interval in which a car approaches, passes, and moves away? Now this is a bit confusing. Students can get tricked by this fairly easily. What most students will choose, well, they know that the as the sound source moves towards the observer, right, approaches the observer, that the frequency is going to be greater, and as it moves away from the observer, the frequency is going to be lower. And students think, oh, I go from high to low. Well, that must mean that it must be A, or rather, it must be B, right? I go from higher frequency to lower frequency, and that is where this common misconception comes in. That's not, sure, it goes from higher frequency, but the frequency doesn't go from 10 to 9 to 8 to 7 to 6 to 5 to 4 to 3 to 1. It goes from a constant frequency of like 10 or something, and as it passes the observer, it goes goes to a frequency of 5. That's how you can think of it. The frequency is not getting lower every second. The frequency is staying constant as it approaches the observer and then changes as it moves away. So the only choice that makes sense, you're going from a higher frequency, like 10, and then instantly as you pass the observer, you go to a frequency of 5. So the correct choice is going to be C. Most students choose B. And this is one of the ways of not being able to get 100 on the physics regions, because they throw in curveballs like this question, right? It's because this requires students to actually think really hard about these questions. And so the correct choice would be C. Let's see how many of you actually watched this video. Um, 3 is something you guys can do yourself. I mean, I'll answer it with you guys, sure. A stationary police officer directs radio waves emitted by a radar gun at a vehicle moving towards the officer. So the source is moving. Compared to the emitted radio waves, the radio waves reflected by the vehicle and received by the radar gun have a what? Okay. Actually, no, the sound source is not moving. So the sound source is a stationary police officer. So we're talking about this. And there's a vehicle moving towards the officer. So we're talking about this GIF right here. So compared to the emitted radio waves, the radio waves reflected from the vehicle and received by the radar gun have a what? So as the observer moves towards the source, the sound waves will have a higher frequency and a shorter wavelength. So D, higher frequency. I would always pay attention to what the question is asking. This question right here is referencing this. The observer is the stationary police source. That's your sound source. As a car approaches a pedestrian crossing the road. So number 4 is referencing this right here, this GIF. The source is approaching the observer. So the source is approaching the observer. So that's number 4. Number 5 is referencing, you guys can figure it out for yourself. Number 5 is referencing same thing. Sound waves are produced by a horn of a truck as approaching a stationary observer. So that's referencing the sound source moving towards the observer. Stationary source located as. It's actually asking you to compare. It's actually making a conceptual judgment. So observer A to the left of S, here's a frequency of 512 hertz. And well, if the sound source has a frequency of 512 hertz, and observer A hears the same frequency, well, he's not moving. He's hearing the same frequency of sound, so he's not moving. Observer B, on the other hand, hears a lower frequency. So what does a lower frequency have to do with? So I would take a look at this slide again. So that's number 6. I would take a look at that slide. 7, moving in a fast-moving spacecraft traveling towards Earth. So again, I would look at this. 7 has to do with this slide. Number 8. Number 8, I would look at this slide. So what has to happen for you have a lower frequency? Right? What has to happen? Or you can actually just yeah, yeah, yeah. Yeah, I would look at this slide. So what would have a lower frequency? 9 speeds up going away from the stationary spectator. So again, I would look at this slide. Oh, this amplitude has to do with amplitude now. Produces sound with constant frequency. As you speak, car speeds up going away from the stationary observer. The sound wave detected by the observer. There would be a decrease in amplitude. There would be a decrease in amplitude. Yeah. And the frequency, you guys can figure that out. If the car moves towards the stationary observer, so I would take a look at this thing again. Let's slide again, see the train moving away. So again, I would take a look at this. The sound source is moving away from the observer. What will happen for this observer to get an increasing frequency? I will take a look at the slide again. Number 13 is asking you whether something would be red shifted or blue shifted. So the green light is moving towards Earth at a high velocity. So if you're moving towards something, you have a higher frequency. And if you have a higher frequency, what color of light is that? Right? So if you're moving towards something, then what's your frequency? You have a higher frequency if you're moving towards something, so what color is that? Good. Cool.